Okay, good morning, everyone. I'm going to very quickly introduce John Blaine. You know, John graduated from UCP and went straight into working as a geologist in Northern Southwest Africa bush at the start of a 34-year adventure with Canadian company Falconbridge. Some of you might have also worked with Falconbridge. Then led to an MSc in geology back at UCT in 1977. That's why I first met John. After retirement from Falconbridge in 2002, he got involved in various other junior Canadian and Australian companies. And sadly, the junior sector is something sadly lack in this country today, but that's for another discussion. Anyway, he's done lots of interesting things, and one of the key things is he actually worked as a exploration geologist in the Kalahari, Namibia, with Kathy Harris' wife, brought up a family successfully, despite of being quite remote at times. And he's moved to Hermanus, much the same year as we did, 2017. And he's part of a very active and widespread geoscientists group in the Overstrand or Overberg. Thanks for coming. It's really great to see so many faces, some new faces as well. So over to John. Thanks very much.
Right. Well, I'm very impressed. I'm very impressed, I must say. And I'm sure it's just the Hermanus beachfront, which is what's so appealing, because it really is. We don't have a beach, but as I say, 2 million years ago, we could have been sitting on a beach, because this was a platform, a wave-cut platform. We'll go into the details of how it happened. It was covered with sand. You can still see a lot of the sand on the surface, but there's a lot of town built all over it. But at that time, there could have been Paleo pre-elephants wandering down over the what's now called Elefantenberg to maybe bath in the flay there where the golf club is now. So that's just how it is. But what you see here is this, what the title of this, which is The Staircase Through Time. And that's a story about sea level change, wave-cut terraces, and how they represent time in a staircase type situation. So repeating that, let me just move this out the way. Oh, sorry. Let me get the pointer here. There we go, pointer. Right, I need to just get rid of that. No, it doesn't.
I think we got the pointer.
Okay, anyway, that's where we are. There's the same staircase, but here's a bit of a representation of how that appeared. Originally, this Hermanus terrace was a marine terrace formed at the base of a fault scarp, which is where the Hermanus fault is now, at the base of these mountains here. And it does cut right across to the Onrus Mountains as well. And the wave energy in there eroded that surface. Sea level dropped during what they call isostatic post-tectonic uplift. So when you get separation of the continents, the lighter continent rises, and we'll go into that a bit further. So that rose up, sea level was further back, and then you had a whole period of eustatic sea level change. And that's really in far more recent periods, and we'll cover that, we're directly related to global cooling and warming ice ages and the development of ice, which drops sea level. Now around town here, in fact, it's now at Seaver's Point, there is this poster on sea level change. It requires quite a lot of intense reading to try and understand it, but it is quite a good record of what's happened here and how it's developed, and it mentions the ice ages. So that's worth hunting out and spend some time looking at it. The diagram on the left there, I have used later on in a slightly different format. So we'll cover an outline, the definitions and representation of these things, the climate and temperature, these Milankovitch cycles, the position in time of South African stratigraphy, what they're made up of with the Bredasdorp group and the Table Mountain group specifically, and how they formed, particularly the Table Mountain group and the Agulhas Sea, climate during those periods, the Gondwana separation. We come to the geology of Walker Bay with the various terraces and platforms. And then finally, what we see on the cliff path, evidence and then sea level change and some conclusions. So these two definitions of isostasy, which is basically an equal sea level equal throughout, but it's the continents that move through to continental uplift, usually a result of tectonic movements, and particularly in the case of Southern Africa, with the separation of Gondwana, that the South African continent being lighter and very granitic cored rose up quite significantly on the underlying mafic or iron-rich mantle. And then you have the other side of it, which is eustasy, which is a result of worldwide sea level change, contrasted with the diastrophic uplift, but it's particularly due to the occurrence of major glacial periods, where ice extracts water from sea level and therefore lowering the level of sea worldwide. So this is that same poster turned on its side. You can identify here, and I must admit, this is a lot of my own interpretation. This has been reviewed by Hayley Cawthra, who is a very well informed on these things, and she didn't shoot this one out the water. So I'm quite impressed with that. But what you see over time, going back 440 million years, is some sequence of irregular historical Paleo before about 30 million years ago, events of ice ages. Back here we have the Pockhouse Ice Age, which is in the middle of the Table Mountain group. Then we all know about the Dwika, which is the base of the Karoo, which was a really extensive ice age. Then we had the breakup of Gondwana, and the whole breakup of which was a start of a whole major drifting of continents around the world, which changed the whole patterns of global sea currents, and that affects climate and everything. So, and that changed the whole pattern of ice ages from being major icehouse worlds to this period where we have a lot more periodic up and down of the Earth's temperature. But during this period, from about 140 million years, when it was towards the end of the breakup of Gondwana, this part of Africa and a lot of Southern Africa underwent this so-called African erosion cycle, which really planed out and led to a lot of deep weathering on many surfaces, whether it's in the Kalahari, in Zimbabwe, even down to the southern coast here. When you drive from Swellendam through to Riversdale, you see these little conical hills through this terrain called the Ruins, which has got a deep weathered profile, and the remains of that silica-rich surface with a lot of siltcrete and ferricrete on it is the deeply weathered remains of that African erosion cycle, which went through and reached a peak, and really was at a peak at about 65 million years ago. But continued through a number of uplifts. There were at least 2 uplifts after that, during the Miocene and during the Pliocene. And you see representations of that on the Tsitsikamma coastline, and I've spoken about that previously. And then you come into this period from about 30 million years ago, where you have the cyclicity, repetition of high level sea level and low sea level related to systematic ice ages. And this is just periods related to major influences on the Earth's temperature. And eventually, at about 20,000 years ago, we had reached the last glacial maximum, where sea level dropped to minus 130 meters, which in fact is the edge of the Agulhas bank, about 100 kilometers offshore. So these Milankovitch cycles, which I believe are the major contributors to these cyclical periods of cooling, warming, partial cooling, partial warming. Nothing is a smooth cycle, but you have at least 4 items here that impact on that. You have these short ones, which are 11-year and 206-year cycles of solar variability. We've just heard about this massive sunspot flare that generates energy which blasts the Earth. And, you know, it comes for a short period. It takes a long time, perhaps, to see the effect of that. You have the 21,000-year cycle, which is the angle of the Earth's tilt. The Earth is not at right angles to the sun. Sun's over here. It's tilted. And that tilt oscillates. It precesses like a top. If you throw a top, It spins fast and then it slowly slows down. That's called precession. And then you have 100,000-year cycles of the variations in the shape of the Earth's orbit. The Earth's orbit is not a circle around the sun, it's in fact an ellipse. So you not only have the close and far distances to the sun as it goes around that ellipse, but that ellipse rotates as well. So those multiple cycles in that. And then you have this 41,000, sorry, that was the 41,000-year cycle, the ellipse, the obliquity of the Earth's axis. So all of these things combine. This has been put together by another group. On the left there, you'll see the reference, talking about global warming as an art project. And there you go. And there, from 1,000 million years ago, they've got these different, beg your pardon, 100,000 years ago, 800, 600, 400, beg your pardon, 100,000 years ago, because that's when the main glacial cycle, the effect of different cyclicities, precession, 19, 22, 24,000 years, obliquity at 41,000 years, eccentricity, and a solar forcing of the effect of the fact that when the Earth goes around on its orbit, it's summer in some areas and winter in the other. And those are the stages of glaciation. So you can see that there's quite a lot of, you can see these correlations coming through of when the combination of everything is warm and places where everything is cold. So you can see these correlations. And that ends up here in the last glacial maximum about 20,000 years ago. So there's a lot of information there to sort of think about. So now let's just step back and see where we are. You've probably all seen this if you've been to Harold Porter, to the Earth Age display of the Overberg Geoscientists. This profile appears, and it's just to show you where we sit in this overall stratigraphy in Southern Africa. The Cape supergroup is in this section here, from the Cambrian with the Table Mountain group through to the Devonian with the Bockerveld group. But the Hermanus Terrace is cut way up here after all the Earth movements that have turned things on their side and separated the subcontinents, and eventually it's eroded. But it's at that period in time, and that's way up in the later, about 2.5 to 1.8 million years ago, equivalent to the Bredasdorp group. So what is in the rocks of the Table Mountain group? If you've been to any of these ones before, this is quite a common feature. Geology, as you may have learned by now, is full of names. We have names for minerals, names for rocks that are made of minerals. We have names for piles of rock. We have names for bigger piles of rocks, and so it goes on. But they all enable us as geologists to identify ourselves in sequence. And the composition of these ones, of this Table Mountain group, is predominantly sandstone. Predominantly sandstone, mostly very clean white quartz sands. There's that glacial horizon in the Pacos, halfway through the Table Mountain group. So this peninsular formation is what Table Mountain is made of, and the bigger hills around here, and these two. The Pacos formation, not well represented here, but you can see it in the mountains going up the valley. And it's one of the only reasons that you can map the Cape Fold Belt from aerial photographs, because the Pacos and the Cedarberg formation are shaly, and that weathers at very smooth slopes. And they're generally quite green and smooth. So with aerial photographs and Google Earth satellite imagery, you can actually map those out. Otherwise, it would be extremely difficult to map these rocks, which are highly folded and displaced, to try and get some continuity in your geological story. The origin of all these sands at that stage, there was the Agulhas Sea was to the south, and we'll show more of that just now. And there was, during the early stage of deposition of the Cape, the Table Mountain group, there was an ice cap. So that Africa, this part of Africa in Gondwana, was situated quite far south. They reckoned at about 60 degrees latitude. So you had, and was not always the same way up. So the Paleo ice cap was to the north now, but in fact was way south of us. So these rocks were being deposited and from an eroding sequence out of this Paleo ice cap. It's quite extensive. It's about 1,200 kilometers along the coastline here and extended up to 400 kilometers inland underneath the Karoo. There are boreholes up here near Beaufort West, which have gone through the Karoo into Table Mountain sandstone. So that was probably what the terrain looked like. It wasn't dark like that because this picture's from Iceland, but they reckon that you had this flat braid plain with these distal meandering streams coming out, decanting into a shoreline and building up these sequences of white quartz sands and very little else. There was a little bit of mud, but there was very little. There may be even on this image in Iceland, you see a bit of moss and algae growing. Quite possible back then I mean, that's those forms of life that already developed in much older rocks. So maybe they were still around, these slimy things that live in water, even in cold water. You know, when you see any sort of slow running stream, you all of a sudden see little slimy patches. And that's the representation of what we expected this coastline and the shallow sea looked like. Here along the cliff path, we'll see this afternoon, you see these amazing cross-bedded sandstones, and that gives you some idea of the direction of deposition and the environment in which it was deposited. And we'll go into that in a bit more detail. So just to step back at the big picture here again, the southern part of Gondwana had this developing Agulhas Sea, which was a linear trough that at the time extended right across from the southern part of South America, across southern Africa, and into East Antarctica. And part of that was, in fact, the Falklands Plateau, which was all jammed up in this large subcontinent here. We look at a cross-section through here, we can see the development of this. And the point here, what I'm trying to understand, when talking about sea level change, it goes way back, going back to that time, 500 million years ago, these rocks were below sea level. Okay, and that's part of the global tectonic movement. Sediments generally are deposited in water because that's the lowest point in the erosion cycle. Even if they are wind blown for a long period, eventually they will end up underwater in an adjoining coastline. So here we had a situation with Africa moving north. The Falklands Plateau, as it was identified, a large body was moving southwards or relatively southwards, and in between the Agulhas Sea was filling, and that opened up, and it's not very similar to the Atlantic in terms of the tectonic cycle that develops ocean basins. It did not separate far enough to expose mafic crust and allow for the intrusion of mafic rocks as you see along all the major oceanic ridges today. So it was like a failed sea. Eventually the cycle turns around and the geological cycle developed by these big mantle plumes and started driving the Paleo-Pacific Ocean plate towards the Falkland Plateau, which was then still attached, and the Cape sediments in the Agulhas Sea started to become folded. And eventually it was shoved up into the air to form a mountain range, which is believed judging by the way these things happened, could have been as high as the Alps or the Himalayas and has been eroded. So these mountains have been eroding for nearly 300 million years. And it's quite amazing. And Southern Africa is quite renowned for some of the oldest mountain ranges. The Milankovitch, for example, is the oldest mountain range at about 2 billion years old. And that's still showing up as a mountain. That's because of tectonic forces that have preserved it. So here we have a representation of what those mountains look like. It's got the Falklands Plateau jammed in there. You've got this Paleo-Pacific Ocean with subduction of the oceanic crust, which is what we've all heard about in plate tectonics. And I've just marked in there where Gondwana started to break up. We do find there are remnants of these same rocks on the Falklands Plateau, but they're not represented here. But that's basically where the Gondwana breakup occurred. So nowadays, a cross-section from the coastline here, George, through to Prince Albert and the Karoo, that's the equivalent part there. All of these rocks have been eroded down. There's still some significant mountains, you know, the Swartberg Range, and then the Great Karoo to the north, all been affected by this Cape Fold Belt folding. As it was being compressed and folded, the Karoo Basin was being pushed down, and this started to erode into that basin, and that deformation continued. And so even in the Karoo, you see remnants of the Cape Fold Belt as it dies out, as it gets further and further away. So once again, you have that cycle. Then you have Gondwana starting to separate. Start separating about 180 million years ago, generally up the east coast here, and that's through a spreading ridge. That created forces that started to split all of this along these major transcurrent faults. And the particular one that affects us here is the Agulhas Falkland fracture zone. That dragged away and dragged the limits of the Falkland Plateau away off the east coast of Natal, KwaZulu-Natal, and dragged it all the way out to where it sits today. And that was more attached to South America, and that formed the Agulhas Bank, because as it was doing that, friction and separation was causing these graben faults, which extend into the Cape Foldberg and form these major basins like the Klein Karoo Basin and the Gumtoos Basin and the Cretaceous Sundays River Basin, that today contain all the oil and gas reserves that have been explored and much spoken about. So this rifting along the Southern Cape Belt were extensions of the Cape Fold Belt, the Agulhas Bank and Walker Bay. Even in Walker Bay, we see remnants of that, and also the alignment of faults in Walker Bay very much along other directions in the Cape Foldberg, not so much east-west, but northeast to north. That's because we're at a nexus here between east-west Cape Foldbelt and north-south Cederberg arm of the Cape Foldbelt. So here in Walker Bay, this is what we're talking about here. We have all these faults that cut through the various units. We have these blocks of granite that have been uplifted. This is the basement of all the Cape Foldbelt sediments in this part of Southern Africa. They are uplifted blocks. They've been uplifted along these major down-dropped faults, where previously, as the definition was compressional and causing thrusting and reverse faulting, and we'll see that later. When they started separated, you had reactivation of those faults into normal faults and exposed all of this. This is Walker Bay. There's a major synform of Bokkerveld rocks, the uppermost units in the Cape supergroup, and they've been preserved downfolded and downfaulted into this. We have upper shales up against granite. And then this is the area around Stanford. This then becomes the Bredasdorp sequence that goes all the way around the coastline to Bredasdorp and Arneson and further on. Now, on a regional sense, this sea level change, once you then got into the glacial cycles, this is now, Gondwana separation has happened. We're now into the different phases of ice ages, cooling and warming. And sea level dropped and exposed all of this sequence of rocks that were deposited below sea level during that period of separation on what we call now the Agulhas Bank. And the edge of the Agulhas Bank is minus 130 meters, and that was the level of the last glacial maximum when sea level dropped to maximum. So 140,000 years ago, it was at that level. It came up higher, and then 20,000 years ago, it dropped again. This has all been extensively mapped and explored by the Council for Geoscience, and largely because this is within South Africa's exclusive economic zone. They had to go and find out. Plus, there had been these oil discoveries. So there's been a lot of work done there. And part of that has been identifying old shorelines. So when you're looking with surface imaging and so on, and able to get cores scattered over it, you can only get a small sample of what that terrain, but a lot of it is coastal, near shore, the sort of same material that we see around Bredasdorp down to Arniston, all the way along the southern Cape Coast to the wilderness. Those very sandy rocks in which there are many remnants of human developments in those rocks as well. But around here, there are at Blombos, Pinnacle Point, and the Kelders, since 170,000 years ago, there's evidence of human development. And the Kelders itself, in the last 70 to 90,000 years, the Middle Stone Age, there are remnants there, and that's been very well mapped and described. So just remember that this was a part of the exposed continent along here from 140,000 years ago. It got flooded during a warming period and then exposed again during a cooling glacial period. And that's provided a lot of information about how sea level changes, how fast it changes, and what we can expect in the future. So this sea level change program called on the Paleo Agulhas Plain was this extensive work done by over the last 15 years by the Council for Geoscience. Haley Coulter has been the main driver. So you've got this broad, up to 270 kilometer broad shelf off Cape Agulhas. It's broad and it's flat and on the outer edges because it's mostly sand, soft sediments that's never been deformed. The middle shelf comes up to about 60 to 80 meters, which is equivalent to Walker Bay. And then a flat inland shelf, which is narrow and is sediment-free and a bit more rocky. So that's sort of cleaned by the current periods of sea level up and down. But on that, they've been able to identify a number of things called nick points, and we'll come across those a bit later at these levels. And particularly in there is this 50 meter level, which is the top of pinnacles in Walker Bay, which we will see later as well. So, those levels all suggest erosion by previous sea level still stands. So you reach a point, the sea's been coming in over thousands of years, and then things are starting to cool again. So the sea is chopping away at the coastline again, and wind is blowing sand off the beaches, developing sand dunes. And don't forget, there are lots of shells in all of those rocks by now, in all of those sediments, and those shells get dissolved by rainwater and gets re-cemented to form these calcarenites or calcareous sandstones, and they are then more resistant. They get really beautifully represented wind-blown sands, fossil wind-blown sands all the way around. Arniston with the Varnes Krantz is a particularly spectacular area. So just repeating part of it there, but during times of minimum sea level, during the Pleistocene, from 1.5 or 1.6 million years to about 1,200,000 years or 12,000 years ago, and during post-glacial periods, maximum sea level rise reached 4.5 meters, or the speed, it rose at about 4.5 meters per 100,000 years. Now they know that from their mapping of the Paleo Agulhas Plain, being able to sample and get the dates on these sequences using using oxygen isotopes on the shelly material which is in there. Oxygen isotopes measure the differences of different types of oxygen isotope in a shell. And nowadays, sea level change is at the level of about 1 meter per 100 years. So it's speeded up. So Walker Bay looks like this. This is a bathymetry map done some years ago of all the contours, the smooth contours like around here, and there, all around this area. Those indicate sandy bottom, and they know that because they've also done surveys, sampling. They drop these like a pipe down it and collect sediment and pull it up. They can map that. And these rough areas, these are rocky outcrops, and these ones come to about 50 meters of surface. So these are a representation of for some reason it was harder and was planed off during one of the last glacial high stands. There's a representation of the Paleoclane River, which flowed all the way out here through a gap. And in fact, there's dolerite dikes mapped, sampled in here from these cores. So there's information in there which we don't see on shore here. And those dolerite dikes relate also to the separation of Gondwana. So now this question of the glacial effects of sea level change, the paradigm is that sea level change is a certain consequence of global warming. However, ice age cycles, the last 200,000 years, have seen sea level fluctuations between minus 130 meters and plus 8 meters. The estimation is that present meltback of all remaining ice on Earth, and you've probably seen lots of stories about how thick the ice is in Antarctica and Greenland, those are the two main ice caps, would create between 58 and 65 meters of sea level rise over an indefined period, which is unlikely to occur. The last time that this occurred was in the late Cretaceous, 65 million years ago, when the plates were all in a different configuration, and particularly the opening of the Isthmus of Panama, before it got closed up by volcanic action along the Cordillera, and the Falklands between South America and Antarctica. That opened up the whole global circulation of the oceans, and the change, this conveyor belt, which they represent as moving cold water from the poles, mixing with warmer water, and that cycle, and that controls our climate. So on a study of past fluctuations from a geological perspective, perhaps in the next 200 years, global sea level could be expected to rise as much as 0.9 to 1.8 meters. And that's a fairly specific number. That indicates that there's a lot of scientific thought behind that. And up to 11 meters in the next 40,000 years. And this is published, Haley Corther and her colleagues. So, they're putting their scientific credibility on paper. So this represents also different periods of sea level change using what they've identified marine isotope stages. This is oxygen isotopes, changes from ratios of oxygen isotopes, and this matches with other models of sea level change represented by different methods. The same thing. So, and the odd numbers here, MIS 11, 5 and stuff, odd numbers represent above sea level, and the other ones are below sea level. So there's the last glacial maximum about 20,000 years ago. And within there, modern human lineage goes back to 60,000 years ago. The later Stone Age, middle of Stone Age goes back to 85, 90,000 years ago. So each flooding event like this would have left its mark on the Hermanus Terrace. And as we can see along the cliff path, similar representations. So we come to sea level terraces. And how do they form? They're generally located, particularly on this coastline, pre-existing strata that could cut right across pre-existing folded strata, which are vertical. Along the Tsitsikamma platform, it's well represented, and that's been planed right off. And you know that when you drive from Port Elizabeth to Plettenberg Bay, it's a flat surface. And there are actually boulders on that surface. Or it can focus on zones of weakness, faults, joints, beds of softer rocks. And it happens by mechanical erosion. The sea, as you know, is just a persistent battering ram. And it exerts pressure on coastal cliffs by standing and breaking waves, and basically at slightly above water level. Maximum wave pressure and glacial erosion happens above the neap high tide. So as you know, neap high tide is the highest of the low tides, and above that is where all the action's happening. And this change and movement, they call it the buzzsaw effect. Just like you see waves coming in on the beach over a long period of time, you can see sea level rise coming in and chopping away, chopping away, chopping away. And it's called the buzzsaw effect on the rocks, and that creates these level surfaces. So during sea level high stands, as currently, absence of a protective beach zone facilitates this process. I mean, this coastline here and all around Walker Bay, we don't have actual beaches except along the Kleinrivier section. So all of these other coastlines are not, the waves hit right on these rocks, and they're continually eroding very minute amounts, and we'll see that. But what we do see inland here are the remnant effects of higher sea levels. For example, in the Onrus Valley, and we'll just go to that briefly just now. So the terminology which has been identified to use in these terrace platform terrace and platform surfaces is that terraces, platforms, benches, and planations are useful geomorphic indicators of coastal processes. You have an erosional notch or nick point, and that's exactly what it says, the sharp edge, and demonstrate a sea level index point for the time of formation. Notches against cliffs are the most reliable approximation of maximum sea level at the time of formation, and terraces generally slope seawards, as the Hermanus terrace does. It's higher, closer to the Elefantenberg, where the Hermanus fault was, and it generally slopes towards the sea. You get erosional, etching, you get these erosional features along lines of weakness on joints, bedding, and faults. And this is quite an important feature along the cliff path, which we'll see this afternoon. And the definition of elevations above sea level require accurate survey of this landward edge of nick points. Now that I haven't done, that's a lot of work. You need differential GPS and all the rest. But actually, Google Earth is an amazing product. With Google Earth, you can draw section lines of topography. And it doesn't matter how long it is, it can be like 5 meters, can be 50 meters, can be 100 meters. And you can click the right button and it comes up with its profile. So Google is measuring altitude in all its traverses. So you can put a line anywhere and click elevation, and it will give you a profile. So from that, I've done 60 sections along the cliff path and got a feeling for what the levels are and what we can see to represent those. And I found that a very interesting exercise. So once again, we're back here at the staircase. So we have a terrace, platform, and bench and planation surface. We have the erosional notches and nick points. And then we have etching that you see from current erosional processes. So finally, we get to what we see on the Hermanus terrace. Sorry, that's taken quite a long while, but it's this time. You know, we're in geological time now. So it started off, and this is a sketch that came from another gentleman who, it's just a representation, but it fits very well to what we see here. During this time, the Hermanus fault down dropped this section here. The mountains behind were left standing, part of the ongoing displacement due to the Gondwana separation, and the sea flooded that area up to the mountains. It created a fossil cliff at the back, which we don't see too clearly now because it's now been covered by a lot of scree coming down off the mountain over the last 2 or 3 million years. And it's well cemented with iron, but there's a lot of sand and boulders and gravel in that. You can see a nice representation on the corner as you go from Vermont around to Houston. There's a quarry there, and you can see a lot of rubble and boulders and stuff cemented in that scree. And the sea level was out here. At a later stage, and that when sea level dropped due to a glacial period, it started cutting a new cliff. But all the rivers that were flowing down off this started to downcut because rivers naturally want to get to the lowest level. That's what rivers do. And you drop sea level and they start eroding down. The Orange River is a classic example, and it creates a nick point. And that nick point on the Orange River is the Agulhas Falls. That's as far back as the Orange is cut since Gondwana separation in that position of the Orange River, and that's another story. So the erosion, that erosion of the Hermanus terrace occurred due to post-tectonic sea level change. Up in the Onrus Valley here, opposite Bartow Eckstein and further up, you get this extraordinary conglomerate developed here on top of Bokkerfeldscheld. That's about 30 meters above the Onrus River. Very rounded pebbles. Here at Newton Johnson and along below Spookfontein, there's also boulder conglomerates about the same height, 25 to 30 meters above the Onrus River. So this represents a level when the river was flowing at that level, probably out onto the Hermanus terrace. Sea level dropped and it cut down and it's left these conglomerates behind. I found that a very interesting representation. So here on the Hermanus terrace, we've got 6 distinct variations demonstrated that correlate with observations in other locations on the southern Cape Coast. And this is in a very general sense. Because as I say, unless you've really measured lots of these nick points, you can't make direct correlations. But I've identified the Hermanus terrace made up of 3 different sections. The inner terrace, averaging at about 41 meters above sea level. The main terrace, that averages about 23 meters. And the outer terrace, which averages around 17 meters. And that indicates the gentle slope of the terrace. Between 1.8 and 5 billion years ago, that occurred, and those are sloping parts of the same erosion surface. Then I've identified what I call etch platform A at about 9 meters, and that's quite a rare one. I've only had 2 observations in all my 60 sections. And correlating with Haley-Corthra's work further along the coast, that probably occurred at about 400,000 years ago. And probably during a period either after the Hermanus terrace was formed, during a period it hesitated going down, or it's come up and then went down again. So that's part of the buzzsaw effect. And then there's the H platform B, which also is not well, I've seen on 7 observations, averages around 6 meters and occurred about 125,000 years ago. That's correlation with what Haley has identified elsewhere. And then what you see a lot of now is what I call the swash zone, between 1 and 5 meters, averaging at 3. And this surface merges, and with it part of the current sea level. It's defined by high spring tides and storm surges. And generally, it's an area where there's no vegetation cover. Not surprising, it's going to get washed out. So absolute ages are not possible because you've either got to have datable fossils. There are other things that have been used, but not so much in these sediments, that have the luminescence of quartz that you can tell when it was last exposed to sunlight. But relative ages are the best that one can do at present without a lot of extra work. So there's my reconstructed section across an average section. So we have the Overberg. Everything looked a lot exaggerated, but when you're dealing with a few tens of meters and singles of meters in this section, it looks a bit stretched. So you have the inner terrace, which is right up there against the Paleo, where the Hermanus fault is, where a lot of our water comes from. You got the middle terrace, and it does have a dip in the middle. And that's quite often because these rocks, once you get down here, and they're the same rocks as you have up here, Overberg formation. That's the same. So those rocks were dropped on the Hermanus fault down to this level. They're generally flat lying, but they're folded. And generally there's a bit of a hollow in the middle here. And we can see that it comes up quite nicely through the middle of the suburbs on the west side of town. And then the outer Hermanus terrace, you've got a number of faults in between. And then on the outer edge here, you've got these A and B etch platforms. And you go into Walker Bay. And further out, there's the Walker Bay fault, which defines where you have Table Mountain sandstone up against Bockerfeld shales. And as you go further east, it's up against Cape Granite, the basement of all these. This SC is the Cedarburg shale. So we don't see it's represented as a smooth weathering surface, but it's been identified in boreholes. All boreholes drilled along the Hermanus fault for water have used the Cedarburg shale as a marker. So these are the sites that we'll look at. Some of these this afternoon, but these are the ones that you'll see in the next few slides. From Rietfontein down here, all the way through. There's a bit of a gap in the middle here. This is Pools Bay area. Through to Dichang and Sivers and Platbank over here. So they all represent different features which I've identified in areas where I actually have been able to draw sections and seen where they are. So it never struck me at first what some of these things looked like, but above Rietfontein, which we'll see this afternoon, you see these funny grooves and channels on this hard sandstone. And they're kind of rounded in between. As you can see, these little hummocks are quite rounded. All these rocks are pretty well flat. And you've got these channels and grooves, and some of them are really intense. And this this patch behind here is at a lower level than this patch in front. And this is elevated because a lot of quartz veins come through there, made it resistant. So what this is, as we'll see later, is extreme etching it's actually on the seaward edge of the outer Hermanus terrace. That's a fairly well-defined elevation of that surface. And that's evidence of wave erosion on this Hermanus terrace, which is one of the few places, in fact, I would say the only place that I've seen this. Elsewhere, it's quite often covered by soil and stuff, and the fynbos that comes right up to the edge. It struck me, the light bulb moment here, you walk to Prickstall. Here you've got these well-bedded sandstones, cross-bedded. This is Prickstall, which is separated here by this fracture or fault. That there is a fault along here. But down here, you can see where the sea washes up, and it's very eroded in these areas, and then less eroded here. And that clearly shows the action of the waves. Even on a little surface like this, that little hydraulic pumping, looking away at these cracks, joints, fractures, breaks out one grade, then the next grain's weakened, and the next one. And that's how mechanical erosion happens, and even chemical erosion. One piece falls out, then the other piece is exposed. And that's why how granites form these rounded boulders as well. Digress. I mean, here's a cave actually on this surface. And this 6-meter etch platform has got quite a well-defined notch here. And Haley likes to identify these as actually a very good place to take elevations because you have rubble that's fallen down. So nothing has happened to that surface since it was formed. Stuff is now covering it up. And that's the same level as this cave. And so it's similar to maybe the cave at Hoy's Copy. When the Hermanus terrace was being eroded, that cave was being eroded. Go further along towards the Kraal Rock. Here or just near Kraal Rock, between Kraal Rock and Grotto, you have this beautiful terrace. It's a beautiful sloping terrace where you can see the current wave swash zone down here, and up here, a generally sloping surface, it's a cross-bedded sandstone, and they've all been etched out on the surface. There's no vegetation, and that I identify as a Paleo swash zone. There's not a single level, but over time, as the sea retreated from down here, it's been eroding the surface all the way down, up and down, up and down, up and down, and here it is still doing that, and just below the cliff edge. So that demonstrates the erosive effect of wave swash as sea level was dropping. If you stand there just near, well, this is at Hermanus Pietersfontein Park. There you look back, and here you can see also seaward sloping terraces, which indicates the height of the wave surge during storms. So these are active erosion surfaces. It always gives me the heebie-jeebies when you see tourists walking around these areas, particularly on the dark rocks, because those ones have been covered by water. And you have these levels. Here's a 6-meter etch platform, and there's the 17-meter outer edge of the Hermanus terrace. And there's our famous Windsor Hotel. And there's a lovely picture. On the left is an old picture of Hermanus. There's the Windsor Hotel. And this was taken in the last few months. And there's the Windsor Hotel. But the terraces are still there. You walk on any of these terraces, you will see those etch patterns. So they are levels where the sea was backwards and forwards. They're preserved. It's chopped out along the bedding planes, and boulders that have fallen off have been taken off. If they're not lying there now, they've been removed by the sea storms, and they're all lying around on the floor here in the little bay. Just west of Fixed Pool, you have this beautiful section which got a number of features of cross bedding, and one can debate what all of these things are. You got the outer edge of the Hermanus terrace. You walk on here, and you don't. I think this is actually Tamati Bonk. You don't see that etching on that surface. It's covered with thin sand, thin orangey sand. But over here, here's a very defined, the 9-meter etch platform. There's an erosional notch with rubble. So this 9-meter etch platform seems to have been a level that is quite well represented. But this section here, where the beds are sloping towards the sea takes advantage of that and ramps up onto that, or has in the past, but still is in storms. And further down below Redfontaine, you get lots of etched surfaces on these flat lying horizons. And this major platform here, where we'll go this afternoon, is really a storm wave swash zone. During storms, the sea comes right up over this. It'll be a bit close to high tide this afternoon, but along this edge here, we see lots of evidence of the remnants of collapse of that cliff and some definition of the height of that, because there's boulders lying there and some massive boulders, and you wonder where have the other ones gone. The sea can damage and take away. So you get the 9-meter platform there, and then you got the outer edge of the Hermanus Terrace there. Here, once again, is that cross-bedded sandstones, which are beautifully etched on the 9-meter platform. It makes beautiful. There are lots of sedimentological features on there, which are fascinating to examine. Along at Sievers Point, people probably wonder about what are these funny pinnacles. It's the only place I've seen them along here. And this is my opinion. The base of this is about the 9-meter edge platform. But those pinnacles probably went up to what was the outer edge of the 17-meter Hermanus platform. And as the sea must have been weaknesses in there, has exposed them and left those standing. And then you get the 6-meter platform out on the edge, those edge platforms. At Kwaiwater, here you can see the 9-meter edge, quite well defined there. It seems to be one that's well represented and easy to identify. Look, the numbers, 9-meter, 6-meter, 8-meter and stuff, a lot more detail, but these are my sort of eyeballing and Google section. And in the foreground here, you've got this open fold, and where you've got swash coming up onto this edge platform here. At Platpunk, a very well-defined surface, about 6-meter edge platform, and then this 3-meter swash zone. This gets covered in stormy seas. So how big is this problem? For us, I don't think it's a problem. Not unless you plan being around here for the next 40,000 years. But in the rest of the world, just recently, there was this data in Visual Capitalist. If nobody follows that, it is a very interesting site. And they had data collected by this interferometer synthetic aperture radar over a 6-year period. And there are 44 coastal cities that are sinking faster than sea levels are rising. Some up to 43 meters a year in Tianjin in China. Measured current rates of sea level rise of the order of 3.7 millimeters per year. You ask, well, how can you measure that? Most rapidly sinking cities are highly populated, megacities built on flat, low-lying river deltas, and we all know many of those around the world, fortunately none here. And this phenomenon is related to compression of rock and soil by man-made structures. We've all seen these huge images, Hong Kong, those coastal cities, and high demands of groundwater abstraction. And we all know in other parts of the world, agricultural areas in the San Joaquin Valley in California, Earth level has dropped as a result of groundwater abstraction. And in some areas, extensive geothermal drilling would have been pumping hot water out to drive electric turbines. And the median rate of change of those 44 cities within 50 kilometers of coast varies between 2 and 16 millimeters per year for the 10 fastest sinking cities. Now, these are clearly related to anthropogenic effects, which exacerbate the wider range of change of 3.7 millimeters per year. So what do we see here? So all the rocks we see around Hermanus were once below sea level, between 500 and 340 million years during deposition. That's the Cape supergroup. And tectonic movements related to the formation of the Cape Field elevated these rocks above sea level. Erosion of these rocks deposited the fragments once again below sea level in the Karoo and offshore since 180 million years ago. Tectonic movements related to the separation of Gondwana since 180 million years ago dropped some of these rocks again below sea level along the southern Cape Coast on the Agulhas Bank and the Paleo Agulhas Plain. Sea level change since 30 million years ago has been the result of cycles of cooling, glacial development, and warming interglacial that caused oscillation in sea levels we see reflected on the Hermanus Terrace and lower edge platforms and the current wave swash zone. These are all features of changes in sea level related to glacials and interglacials. So repeating, sea level fluctuations in the past 200,000 years have ranged from from minus 130 to plus 11 meters. And perhaps in the next 200 years, global sea level could be expected to rise as much as 0.9 to 1.8 meters and 11 meters above present in the next 40,000 years. And that's published and described to me personally by Haley. So this is a natural process, and although human impact may enhance or accelerate the rate of rise, climate change and sea level change is a natural process. So thanks for that. And if nobody has been to Harold Porter, you need to go and update your knowledge of Earth's history by this amazing display. And then this afternoon, we'll be covering this. I've called it deposition, deformation, and erosion. It's a very short walk, take about an hour and a half, 2 hours maximum.
Okay, thanks, John. That was excellent. I mean, I think probably the one thing John highlights is that we live on a dynamic Earth. You know, we get hugely misled by all the political hype about global warming and climate change. And what John has just showed you, and we have this amazing example of climate change which is ongoing. And we have these beautiful examples on our doorstep. And as he said, most of us who live in Hermanus and Vermont and that are living on an old 30-meter beach. So, you know, climate change happens and sea levels go up and down, and they've done that for millions of years. And John showed you the Agulhas Bank, which has been mapped, and we have one of the, were you Andre? We have one of the sort of leading marine geologists in this group. Where's Andre? He's hiding at the back. Stand up, please, sir. Okay, so these are the sort of people who you know, did all this amazing work on our coastline and out at sea. So Andre Duplessis is an old hand at it, and John mentioned these fascinating young people like Haley Cawthra, and we've had a talk here, had her talk here before. And when she comes again, come and listen. She's just an amazing resource, South African girl from Durban. Okay, so we have all the talent, and we don't realize, you know, how many of our minerals, resources, all of these faults that we have and the aquifers that we use. Currently, Greater Hermanus gets about 35% of its potable water from aquifers at the base of these White Mountains. And part of that's because of the breakup of Gondwana land and the structures that happened, and the bottom of the TMS, which got fragmented and fractured and stores billions of liters of fresh water and old water. We've mined alluvial diamonds, high quality alluvial diamonds on our west coast and the Orange River. And there's Mr. Hazel at the background, who was very much part of De Beers in those mining. And that again is because, you know, the land surface has gone up and down, the riverbeds have shifted, and we get drowned beaches offshore the west coast of South Africa with diamonds, and we get old beach terraces onshore that have been extensively mined. In fact, next year, 2025, is the centenary, 100 years of mining diamonds on our west coast, and we'll do a presentation about that. Maybe get Mr. Hazel to give us some insight. Okay.
How rapidly that, how deep does it get?
Well, it goes down on the abyssal plain, and as we know from work but those rock units that contain oil and gas continue out that far. Okay? So Total was planning to drill in 4,000 meters of water and probably go down another 2,000 or 3,000 meters to the reservoir. That's part of their challenge, because it's when Andre can probably correct me, when they discovered that, and that was not from, I think, from drilling, but from seismic work or from geophysical work, just operating in the Agulhas current, which is one of the fastest flowing currents on Earth, you know, where it's kind of meeting these major fronts coming up from the south. The technological challenges of operating like that on top of the political challenges, it just said, I'll do it. And that's our loss.
And just put that in perspective though, John, I mean, the actual Agulhas bank is very shallow. You know,
Yeah.
Haley's dived in it. How deep is
It goes to 130 meters.
Yeah. So, you know, you can go down there and swim on it and see exactly what's going on. So that again is just this ongoing sea level change where the oil deposits are 60 kilometers off our shore here. Obviously there you're on the shelf, on the edge of the shelf and getting much deeper.
Then you had this fellow remark about getting the EBGBs when visitors walk on your rocks. What was that sort of about? For their sake?
Who's got the heebie-jeebies? No, look, I mean, anybody walking on the cliff path, particularly when you have strong winds, should be very aware. Sorry, you mean what I mentioned? Yeah, I mean, I get the heebie-jeebies, particularly around Gary Point. You see people, I've seen people going right off onto Castle Rock at low tide. But you know, you never know when a wave is coming through. They're not fishermen. They're not people who are water aware. It's
Well,
stupid.
sadly on that, was it a year or two ago, the rugby player's mother,
Yeah,
there were two ladies of color who went down into the old harbor, stood on the edge and
on the wall,
taken off by waves. So, you know, we all know we're fortunate we've had that experience. The sea is not to be played.
But yeah, that's
And Mike Normal wants to know, are the 6 and 9 meter thick points at Overberg, the nick points, and are there different down drop sections?
No, Mike, those nick points are erosional nick points. And they're generally, whatever the thickness is of the bed of quartzite sandstone above it. And that would be a measured level or a interpreted level from Google Earth sections and my visual observations of those points. There's no stratigraphic difference that I can see on, because I mean there's all Overberg rocks along here, and who can tell one Overberg rock from another one 20 meters up or down? It's quite a challenge.
But those are also sort of sea level stands, so that beach cuts a little ledge there.
Mark Coulthard says thank you very much. He'd like to come and join you on a walk on.